Hello, I'm Sebastian. Welcome to 9 Trees podcast. Today, I will summarize and review the book. Probability and Statistics for Engineering and the Sciences by J.L. Devore is a widely used textbook that builds a practical bridge between mathematical probability and real engineering and scientific decision-making. The book is designed for students who need both conceptual understanding and the ability to carry out statistical analyses on real data. It typically begins with the language of probability, random variables, and common distributions, then moves into core inferential tools such as estimation, hypothesis testing, regression, and analysis of variance. Throughout, the emphasis is on modeling variability, quantifying uncertainty, and interpreting results in context, skills that show up in quality control, reliability, experimental design, and data-driven research. Readers can expect a progression from foundations to applications, with worked examples and problem sets that reinforce methods and reasoning. The overall experience is that of a structured, engineering-oriented pathway from uncertainty to evidence-based conclusions. I will give you key takeaways from this book. Firstly, probability foundations for modeling uncertainty. A central theme of the book is that uncertainty can be described precisely, and that good models start with a clear probability framework. The early material typically develops the basic rules of probability, counting techniques, conditional probability, and independence, because these concepts are the building blocks for almost every applied method that follows. Engineering and science problems often involve systems with multiple components, sequential events, or partial information, and conditional reasoning is essential for interpreting sensor readings, test outcomes, and diagnostic signals. From there, the text usually introduces random variables and their distributions, focusing on expected value, variance, and other summaries that connect probability to measurable behavior. This foundation supports practical questions such as how variability accumulates, how rare events should be assessed, and how to choose a probability model that matches a physical process. The payoff is not just computational skill, but modeling judgment, knowing when assumptions are reasonable, how to translate a narrative problem into a probabilistic structure, and how to interpret probability statements as operational guidance for design, monitoring, or risk management. Secondly, key distributions and the role of sampling behavior. Engineering statistics relies heavily on a small set of distributions that appear repeatedly in applications, and the book typically gives them careful attention. Discrete models, such as the binomial and Poisson, connect naturally to defect counts, event arrivals, and reliability events. Continuous models such as the normal, exponential, and gamma families are often used to describe measurement error, lifetimes, and waiting times. Beyond listing formulas, the text usually emphasizes when each distribution is appropriate, how parameters influence shape, and how distributional assumptions affect conclusions. A major step is linking population models to sampling, introducing sampling distributions and results like the central limit theorem. This is where probability becomes directly useful for statistics, because it explains why averages stabilize, why standardized statistics follow certain reference distributions, and how uncertainty in an estimate depends on sample size and variability. Readers learn to think in terms of repeated sampling and long-run performance, which is critical for quality control plans, calibration studies, and experimental comparisons. The focus on sampling behavior sets the stage for confidence intervals, tests, and predictive statements that are defensible in technical settings. Thirdly, estimation and confidence intervals as quantified evidence. The book commonly treats estimation as the first major inferential task, using sample data to learn about unknown parameters while explicitly stating how uncertain that learning is. Point estimation techniques are presented with criteria such as unbiasedness, efficiency, and mean squared error, helping readers understand what makes an estimator good beyond convenience. Interval estimation then adds a practical layer, providing confidence intervals for means, proportions, variances, and differences between groups, often under normal or large sample approximations. In engineering and the sciences, decisions rarely hinge on a single number, so interval estimates can be more informative than point estimates because they communicate plausible ranges and precision. The text generally highlights how interval width depends on variability, distribution assumptions, and sample size, and how to plan data collection to reach a desired level of precision. Another valuable emphasis is interpretation. A confidence level is about procedure performance, not a guarantee about one realized interval, and misunderstanding this can lead to overconfident claims. By working through realistic examples, readers develop the habit of pairing an estimate with uncertainty and using that pair to guide design tolerances, performance claims, and research conclusions. Fourthly, hypothesis testing and decision-making under risk. Hypothesis testing is usually presented as a controlled way to make decisions from data while managing the risk of wrong conclusions. The book typically frames tests in terms of null and alternative hypotheses, test statistics, rejection regions, p-values, and error probabilities. Engineers and scientists often need to decide whether a process has shifted, whether a treatment changes an outcome, or whether a new material meets a specification, and formal tests provide a transparent method for such decisions. The text generally emphasizes Type 1 and Type 2 errors in power, showing that a test is a design choice with trade-offs rather than a one-size-fits-all rule. This perspective helps readers select significance levels based on consequences, not habit. Many applied settings involve comparing two populations, paired data, or multiple groups, and the book commonly covers these scenarios, along with assumptions such as normality or equal variances and the consequences when assumptions are questionable. The practical goal is to connect evidence to action, deciding when the data justify a change, when more data are needed, and how to communicate the strength of evidence to stakeholders responsibly. Lastly, regression, experimental design, and variability in systems. A major strength of an engineering-oriented statistics text is its coverage of relationships between variables and structured data collection. Regression methods, starting with simple linear regression and extending to multiple regression, help quantify how inputs relate to outputs, assess model fit, and make predictions with uncertainty. The book typically discusses residual analysis and diagnostics to check whether a model captures the underlying pattern and whether assumptions such as constant variance or independent errors are reasonable. This connects naturally to analysis of variance and factorial experiments, where the goal is to separate signal from noise and understand which factors and interactions materially affect performance. In practice, these tools support process improvement, product development, and scientific inference because they turn data into interpretable models rather than isolated summaries. The text often emphasizes planning experiments to maximize information using randomization, replication, and blocking to control confounding and reduce error. This topic area is where probability and inference become a full workflow. Define a question, collect data strategically, fit and validate a model, and then use that model to optimize, predict, or justify engineering decisions in a way that is both rigorous and practically communicable. In conclusion, this book is best suited for undergraduate and early graduate students in engineering, physical sciences, and applied fields who need a complete first course in probability and statistics, as well as professionals who want a structured reference for core methods. Readers benefit because it ties mathematical foundations to the kinds of questions they actually face, modeling measurement variability, estimating performance with uncertainty, comparing alternatives fairly, and building predictive relationships from data. Those skills translate directly into better design choices, clearer research conclusions, and more reliable operational decisions, whether the context is manufacturing quality, laboratory experimentation, reliability analysis, or data-driven product development. Compared with many similar books, Devore is often chosen for its balance. It is mathematically careful without losing sight of application, and it typically provides a coherent path from probability concepts to modern inferential practice. The progression helps readers build intuition rather than memorizing disconnected procedures. For buyers, the value is that it can serve both as a course text and as a long-term desk reference, supporting repeated use across projects and later coursework in areas like quality engineering, reliability, and applied modeling. If you would like to support J.L. Devore, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.